Hello, everybody. So this is another live coding session here with Jeff, and so I'm going to take a break from talking about assignment 2. I think we've gone far enough along with that, and kind of want to wind back to assignment 1 and talk about my solution to this, and maybe sort of address some of the most common errors or missteps, I guess, that people might have made along the way working on assignment 1. I know everybody's new to C++. Of course, we don't know everything about how to deal with that, and many of you are probably really just getting started with programming. So mostly this is just sort of intended as a nudge in the right direction to sort of get you thinking about some of the things that that you might be thinking about here. So this is my main.cpp. You'll notice actually at the top here that I have these define statements. Now we haven't talked about these really at this point. These aren't really essential. Basically all these are just a bunch of constants with names that I can use in my code. I'll mention these again when we get down to them. Other than that, there's these two functions that I made up for myself. We talked a whole bunch about how to print out the table that you're interested in, both for the console and for the file. And so there are a couple of things that you might want to do to this if you wanted to kind of make it more general. Now, I know probably for many of you that involved copying this code around a few different places or just sort of leaving it in your main loop, which is all pretty fine, but you know, I am trying to give you examples of like how you can work on sort of generalizing your code and moving things into functions so that, you know, everything stays pretty organized. What I've done here is I've made a couple of functions, this one being get formatted table header. So what this does is it gets me as a string a table header, and given that I pass it in a string that is a separator. And so if you'll recall, we used either comma or a couple of tabs to separate our things. And in fact, you'll notice if I just jump down to a place where I'm using this, get formatted table header, so there are times where I'm passing it a comma, and there's times where I'm passing it tabs. And so actually in this case it's a single tab, I believe down below tabs here for table row, but similar. And so in the case of get formatted table row, I have a function that takes a bunch more things because it needs to be able to print out a time, it needs to be able to print out the x component of the force, and it needs to be able to print out the x components of the acceleration, velocity, and position of the body. So I need to be able to pass these things into this function, and then lastly, it also takes a separator to sort of break this up. And so another thing that you may be a little bit unfamiliar with in here is this string stream. Don't worry about it too much. This is a slightly more performant way of mashing strings together, but perfectly satisfactory to not use this. I'm just sort of in the habit of doing so. Basically what a string stream does is it gives you a really performant way to concatenate a bunch of strings together, and then when you're done, you can output an actual string object from it. So that's what I'm doing. But so this is how I go about formatting my tables here, and it's really not that different from what you guys are doing using this in place. Probably the only big difference is that I'm passing in this separator, and so if you wanted to, your separator could be a period, your separator could be a space, your separator could be all sorts of different things depending on whatever maybe you need to do. But in my case, I'm using commas or tabs, and this function does everything that I need without a problem. So kind of how I wind through the main simulation. So I've got my main here. Is I start off, I set a file name here for my output stream. So I create my output file stream like right away. That's like basically the first thing I do, and then I write my table headers both to the file and to standard out so that it appears on the console. Secondly, I create my force vector, and I create a body using this define. So this constant body mass. I said that I would come back to these, right? So this is one of these that's up top here. The reason that I've done this is that I wanted to make a place in my code where I could go to easily change values if I wanted to play around with the way that this thing flows. If I needed to change the mass of my jet ski, I could easily do so. I could change it to 300 right here, and it would just automatically sort of take effect, and I wouldn't have to fish around in my code for where that number was set, which could be kind of hard if, you know, if there wasn't something to find it. Now, mind you, we don't have, we got like 100 lines of code here, so it wouldn't be that hard to find, but as you can imagine, once you start getting into bigger programs that are talking like 10,000, 20,000 lines of code, if you need to find something and change it, well, that's starting to be a little complicated. So, of course, so I have my current time. Obviously, the start time is 0. I could start the clock not from 0. That would be weird, but I could. And then I have sort of my main simulation loop. So this is the bread and butter of what goes on in here. And the way that I chose to do this, the way that I chose to approach this was to have a couple of if statements in here, checking for different things. And mostly I'm going based on time, right? Like, because we've got up until 5.5 seconds, you're applying 500 newtons positive on the x-axis to the jet ski. And in the time between 5.5 and 10 seconds, there's no force applied, setting that to. And then after that, I'm applying the stop force, which I have set at negative 625 newtons. That causes you. So, I mean, of course, you can see up here, my start force is 500 and my stop force is 625. So now, this is the first thing that I want to bring up. Is that when I was looking through people's solutions, I saw a lot of people who were testing for when the time is exactly equal to 5.5 seconds, for example. And so something that might look like this. And you might think that, well, this is really sleek because that means that, okay, so if the time is ticking upwards in, 0.5 second increments, let's say, I think in my case, I have my timer set to tick at 0.1, but either way, it would, at some point, you'd think it would hit 5.5, and then this one line of code would run, and then when it gets to 5.6, it wouldn't run again. It's really clean and sleek, and, like the logic prevents it from running more than necessary. Not quite, or at least not necessarily. Floating point numbers are a little bit inaccurate on computers, and when you are testing to see if a number that you've done some math on that should be equal to 5.5, if you want to test that it's equal to 5.5, there is a chance that it will be slightly off, and your equality statement will break down, which would then mean that this force never gets set. And interestingly, this could work fine. Your code could work fine with one time step or maybe a couple of different time steps, but certain numbers might cause your code to break down. Putting your code onto somebody else's computer and running it might cause it to break down. Very strange things could happen. So my advice is to stick with greater than or less than equality statements. Greater than or equal to, less than or equal to are both also okay, but the most important thing here is that you're sort of testing everything in a particular direction, either greater than or less than. The reason that I do this is, now mind you, my decision to do this causes this force.set to get called all the time when we're less than 5.5 seconds, but I'm safe in knowing that there is no way that this will like break down or not run. So somebody ought to ask the question, why? Why do computers work weirdly like that? Well, okay, so my best advice is that, here we go, the IEEE floating point arithmetic standard. That doesn't sound like a whole lot of fun to read, but my suggestion is that as a programmer, you should probably at least read over the Wikipedia page for the IEEE floating point number. This is how floating point numbers are implemented inside computer hardware, and they work in sort of interesting and weird ways. So, for example, like the typical one that you'll see, float, for example, in C++, usually refers to a single precision number, which can accurately store about 7 decimal places of accuracy. But the numbers that it represents don't necessarily fall like on nice lines in decimal numbers. Like if you type the literal 5.5 in, that may mean to the computer 5.5000002, something like that. It's very close, but not quite. So in any case, I'm not going to go into depth on this because it's a fairly complicated subject, but I do want you to be aware that floating point numbers do have an inherent inaccuracy, which is well within the tolerances of what we need for doing most game development things, but that if you're testing if two things are exactly equal to one another, it can be off by the slightest little bit and cause you a lot of problems. So this is a thing to watch out for. So try to stick with greater than or less than statements when you're talking about floating point numbers like this. I may talk about another strategy that you can use to do something like an equality test for floating point numbers, but I'm not going to cover that. So continuing on here, so I've got my if statements that sort of select what force should be applied based on what time we're at. And once I know what force is going to be applied, I apply it to the body. I print out the body's state right now, and time table out there. Then I update the body. And I'm going to delve into this in a moment, because there's another common mistake that occurs around this as well. And then, of course, lastly, I update the current time with my delta time. So the most actually, no, let me rewind 1 minute. I update my current time by the delta time, but you'll notice that I used a do while statement and my exit condition doesn't actually use time at all. In fact, it's totally unnecessary, because if I go through this loop one time, my velocity should already be higher than 0 on the x-axis because I've applied some positive force, and the loop will continue until my velocity drops back below 0. So this allows me to continue on powering the jet ski until eventually this stop force at negative 625 newtons pushes my velocity back below 0, causing me to stop. And to accomplish that question that I was asking many of you for, that would be as simple as just switching this number to -2, and like that, the loop would just continue until it gets to that point. Okay, so rewinding, we're going to talk a little bit about this body update. There was a little bit of confusion here surrounding what to do with update, and probably the most current or the most common mistake that I have seen that is actually a problem and that will cause your simulation to do weird things is sending the current time to body update instead of using delta time. So now this is not super obvious at first, in physics, and to be honest, this comes down to a statement that only shows up on one slide. Um, do you remember when I talked about how the equations of motion are only valid for constant acceleration? Because the body is having forces applied to it that change through time, we can't use a single equation that is computing from the start of, like, from zero time to figure out its position in any, like, really good way. Because the acceleration is one thing from 0 to 5.5, and it's something else from 5.5 to 10, and it's something else after 10. So one equation would unfortunately break down. The equation that many of you are probably thinking of would be that, like, velocity times time plus acceleration times time squared 2. That is often an equation people will use to come up with a position for the body, but in fact, I'm going to show you that it's a little bit simpler than that. Actually, as I do that, I want to introduce you to a couple of hotkeys that are really helpful. Did you know that F12 is your greatest friend in Visual Studio? F12 and a couple of, like, Shift F12 and I believe Alt F12 and possibly even Control F12 are all really handy. So notice that I've got myself clicked on body.update here, right? So I've got update highlighted, F12. Boom, takes me right to the location of the definition of that function. That is tremendously helpful. But another thing that I can do, in fact, I believe it's Alt F12 for this one. So if you have Visual Studio 2015 or later, Alt F12 will open this little panel where it will look at the file. So this is gdbody.cpp that it's looking at, and it will just sort of show me a little window, like, in place right next to this, so that I can kind of see what it does, like, right there and within the flow of the code here, so that's really good. So that's Alt F12, so you know. So you'll notice that the way my body update flows is that I'm updating the velocity by using plus equals. So this is the same thing as velocity equals velocity plus delta time times acceleration. So I'm multiplying time by acceleration, and of course, acceleration times time gives me a velocity. So this is my change in velocity for this time step, for this sliver of 0.1 seconds in my case, and I'm adding that to the current velocity. So my current velocity that I have on the body is referring to how fast I was going at the last instant that we simulated, and now we want to simulate one little chunk more. So we will be using this delta time and passing in this little time sliver. And by doing this, all the equations that we use are valid for that time sliver, because that's the smallest unit of time that we can simulate for. Accelerations have to be constant over that period of time. And so this will always lead to at least an okay result. It's not perfectly accurate unless you can simulate time at, like, an infinite frame rate, but it's close enough that nobody notices anything's amiss. So I'm adding delta time times acceleration to my velocity, and then once I have my updated velocity, I'm using time times velocity to add to my position. So of course, velocity times time, the distance or displacement, and so that gives me an update to my position. And then lastly, I had mentioned this before, is that we need to zero out the acceleration, because the acceleration is being computed by the force that's being applied on a frame by frame basis. If we don't clear acceleration, then this number will get to be very large and weird over time, and it will do very strange things. So now, there was a tendency among some students to push some of their logic surrounding things like what force to apply into this update function. I discourage doing this. Um, the way that I like to think about it is that your body class is something that is general. Your body class is something that you could conceivably bring to another program and just drop it in and be able to use it for what it does. If logic like this starts going into your update here, then you have tied the needs of this program into your body, and it may function really weirdly for some other situation. This is one of the sort of central challenges of programming, is trying to figure out where certain code should go. And so for reusable classes like GD body and such, where you know you might be able to move them to another program and use them, we should really make every effort to ensure that they are programmed in such a way that we could do that. The instant that implementation specific or application specific codes, you'll hear me say that from time to time, code like this that is tied really strongly to the scenario that we're playing out here should stay out of that class. Now, it's going to take a little bit of time and experience to see those situations as they come up. And I realize that there's not really an easy way to tell you exactly when it should or shouldn't be that way. But as time goes on, you'll start to spot this stuff, and you'll start to probably have some stronger opinions about where code should or shouldn't go. And it may disagree with other people that you know. You might end up in arguments about it. I've seen it happen, and it's not unusual for people to have different opinions about how programs should be designed. But there are some good rules to follow that everybody can generally agree on, and more or less it's important to keep code that needs to be reusable from being polluted by application specific things that make it useless in a general situation. So again, like, this is your first program in C++ working in physics, so I mean, I don't necessarily see this as bad, and I'm not going to like take serious marks off of anybody for this, but this is a thing that we should be working on, that everybody should be trying to think about this in the future, and think about your choices about where you put certain code, because it's not necessarily only about making it work. Want to be able to go further than that, and this is one of those ways that you can write good code that you can reuse. So there's that. So escape just exits out of that. Of course, lastly, I come to a stop by after my while loop ends, and I'm at a stop. I set my force to 0, print my last row of the table, close out my file, and then I just wait for key press so that I can continue to see my console. So there were many different ways of coming at the way that this loop works. So my initial choice was to do something with this. So I have one loop that runs through and ultimately just checks for velocity, and inside that loop I make decisions about what force is being applied with an if statement. So now this results in the downside that this force.set is being called every frame, even though it doesn't really need to. It really only needs to be called once to set the force one time until we get to 5.5 seconds, when the force gets set to 0, and at 10 seconds we need to set the force to -625, right? So this works fine, but it also has a couple of like cons. There are pros and there are cons to doing any particular sort of thing, and some of you may have approached this a little bit differently than I have here. So I wanted to show something different that I concocted that is doing the same thing that this is doing, but it writes it in a slightly different way in order to be able to emphasize that there are a lot of different ways to approach a problem like this. And they have sort of different strengths and weaknesses. So, okay, so I just pasted a big chunk of code in here. So, okay, so I just added in, here, I'm going to close these while loops up so look at this. Right, so basically this is my replacement for the do while loop that I had in there. Now, so what I've done here is outside my loop, I'm setting my starting force. And then I have a while loop that runs until I get to 5.5 seconds. So coast time is 5.5 seconds. So it does applying the force, exporting, like dumping the table out to the console in the file, updating the bar, updating the. And then once we hit 5.5 seconds, this loop breaks. It gets set to 0. Let's do it again, but this time we'll run. Time is we will run while current time is less than stop time. So we're just doing exactly the same stuff in either of these cases. Nothing's really changing about what's going on. It's just that in this case, current time left off being equal to or greater than coast time, and now current time is continuing on from that point. So then we continue on until this breaks when we hit 10 seconds. Then I switch the force to be the stop force, and this time I run my loop until my velocity is smaller than or equal to 0. So while my velocity is greater than 0, I continue running. And again, I'm doing all the same stuff in here. So one way that you can look at this is like, well, okay, so is this more or less complicated than before? Well, what I have written here is certainly more lines of code, but it's also nice that this force only gets set at the times that it really needs to be, and it really makes it clear that there's 3 steps to this, whereas my previous code, the way it was written was a little bit hard to tell, because there was this if statement inside that was doing the work to figure out what force, and that wasn't really enough to tell me, just looking at this code, that there's like 3 major phases to this thing that's going on. So I mean, this has some readability benefits, and probably the only downside to the way it's written right now is that it's longer. It's more lines of code, and in fact, there are a bunch of lines of code here that are entirely repeated. And when you see that, that should be a good signal to you that it's time to write a function for something. So, why don't we? Let's just do that. I'm trying to think, what do we want to do with this? We probably have a void function, and we're going to need to pass it in. We're going to have the current time, the force, the body, at least. Okay. So, I'm putting these functions above, by the way, because in C++, by default, if the functions are in the same file, like if it's not a class with a header file, it needs to see them defined before this, or it acts as though they don't exist. So if the function is below, it doesn't know about it yet. So that's a thing to pay attention to. Let's just call it steps. So this is for one time step. We're going to pass in a double current time, and we're going to pass in a vec2, or I guess I should make this a const vec2. It doesn't have to be, but it's better. What this const means here is that I'm claiming that I won't change force when it gets passed in here. I'm also going to pass in the and that might be all the stuff that I need. So, yeah, actually, I'm not going to call this current time, I'll just call it time. So it shares exactly the same signature as the get formatted table row, more or less. It's very close. So you'll notice that this step function, I copy these things. So this step function is going to be running these lines of code. Oh, okay. All right, there's one line that I don't want to include here. It will make things a little. So oh, this may not be. Yeah, of course. Yeah. So the body is in fact changing here. My statement const GD body reference. I should zero in on this a little bit. So you'll notice that the compiler is actually doing some things here to tell me that I am breaking the rule that I made here. So when I say here const GD body reference, what this is meaning is that I will not change the body in any way. However, if I call a method like this on the body, the compiler has reason to believe that I might be changing it. So I want to, and in fact I do want to change it, right? The purpose of apply force to center is to change the acceleration of the body by applying force. An update's purpose is to change the velocity and the position based on a change in time. So this const should go. That's got to go, because our intention with this function is to change the body. That's the point. So current time is here, and oh, of course, I guess I'm going to have to pass in my file stream because standard stream file stream. Right, and so we're passing the time in, and good. So that's what a step looks like. So then let's use it. So I'm just going to replace all this stuff. So I'm going to pass current time in, passing the force, I'm passing the body, and I'm passing the output file stream in. I should probably pass that as a. Generally, you want to pass objects as references. Most of the time, you don't want to copy them. It's yeah, it's a thing that you'll learn more about as time goes on. Hard and fast rule, but not the only one. So now that I have that in place, look at how much that cleans things. Look at how much that cleans things up. So now I have these little while loops. Okay, continue doing this until we get to coast time. And just each time we know that we're going to use this step. It's going to be the same way in every case. And to be honest, I could even go a little bit further than this. If you wanted to compress the lines down, you could use a for loop. So, interesting fact, nothing has to go in the, like, before this semicolon. Like, you don't have to initialize a variable with, just leave it if you want to. So my initialization out here of current time, like, that's fine. So then I can say current time is less than coast time, and then I can just put this statement right into my for loop if I want to. Yeah, alright. I'm gonna bring this up while I had it. Did you notice that I had this semicolon sitting here? I didn't run the program, so I didn't see anything go weird. But actually, what this means is this for loop, or, well, actually, let's look at this while loop because we're more familiar with this one. So this current time is less than stop time, semicolon end. What that means is while current time is less than stop time, don't do anything and continue the next iteration. Really, kind of what I'm looking at is something like this, that this line will execute as a loop forever and just lock your program. This is a terrifyingly complicated error to find. You will probably think to yourself, it's only one character, those are the most horrible errors, like, you feel so dumb. No, Don't feel dumb. One character errors are those that are the hardest to spot. This would be a terrible error to have happen to you. Be really annoying to come up with. On a separate note, putting things in brackets like this, yeah, that's valid syntax. That actually works. We might talk about that later, but now. In any case, make sure those semicolons on the end of those disappear. And so then, yeah, let's apply a similar syntax to these. So we'll just put the semicolon in here. For front, and that means that I can drop that current time, I can drop that current time, and well, I mean, I guess technically I can do the same thing here. The condition in a for loop doesn't actually have to do with it's not essential that the condition in the for loop actually match the thing that's being counted. That's not important. Look at that. So now we've stripped this down to be quite a short process, and it's doing everything we need it to do, and the step is sort of encapsulated into its own, which is kind of comforting in itself. I like that. I've said to a couple of people, it's ideal if your functions never go over about 50 lines. Some people even use tighter restrictions than that. Some people have feelings that functions should be less than 25 lines or 20 lines, because even 20 lines of code can get pretty complicated sometimes. So you really want to think often about ways that you can sort of break things down into smaller functions that can be reused in useful ways. And this is one of them. So yeah, this is basically where this went. Other than this, so I've shown you the update. We already had apply force to center. Most of these things were done and good, I think. And that's right. So we have this vec2, which I am going to talk about more soon in the lead up to assignment 3. I'm going to be discussing with you in the next couple of weeks the idea of using matrices to transform objects from their physics coordinates to screen rendering positions. So I'm going to be working with Scott and Humber a whole bunch to work together our courses so that your C++ course and our physics course line up, and we're going to be delving a whole bunch into that near future. So look forward to using a bigger, fancier, and building a bigger, fancier vector class, learning how to use matrices to multiply your vectors to do all kinds of cool stuff. All right, I guess that's it for today, but thanks for watching, and I'll see you next week.